Good afternoon, guys. Thank you for showing up. Even with this rain, you are able to show up. That's really great. So myself, Shubham. I will be taking the first discussion session of this week, and the second half will be taken by Aditya. So let's go over the logistics before we start. So this homework 2 is due by Thursday, that is 25th of January. A couple of announcements before we move ahead. So we have updated the problems a little bit for homework 2. First problem is changed a little bit, that is the SCC one. Please check out the new files that's uploaded. And also problem 3. If you guys have already seen that problem, that you might remember that in that question we asked you to find a trail going from S to T, right? So we have changed that to walk now. So for homework 3, question 3, homework 2, question 3, we are changing this trail to walk. That means you can repeat the number of edges as well. Okay. So initially we had the restriction that you cannot repeat the same edge twice, but now you can do that. So we hope this will reduce the complexity a little bit. Any questions? Okay, great. Please join office hours. You can see the schedule on Canvas. And also, we have also opened one-on-one slots, the link for which you can see on Piazza. There is a Google Sheet where you can sign up basically. Okay. And also feel free to ask any question that you have on Piazza. And during today's discussion, please feel free to interrupt me anytime you have any questions or anything. Okay. I hope everyone in the back can hear me as well. So we will be solving this problem today. We will see like how to approach it right from the solution. Then we'll go over the proof a little bit, and then we'll also look at the runtime of this problem. So it will exactly be how you are supposed to solve a problem given in your homework. Okay. So the problem, it goes like this. So you are given a simple directed graph G with vertex set V and edge set E. Along with that, you have also given some edge weights, and you can only have either 0 or 1 as your edge weight. And you're also given a starting vertex S and a ending vertex T, or a terminal vertex V, T. So the question is, you need to design a reasonably efficient algorithm that determines if there is a walk from S to T such that sum of all the edges is even. Okay. So let's see an example before we move forward. So in this first problem, so do you see a walk from S to T where the sum of edges is even? So if you go from S to A, then A to C, C to B, B to D, and then D to T. So you can see like we have encountered 2 red edges, that is the edges labeled 1. So yes, so this one should return actually true. What about the second one? Yeah, I can see some nods there. Yeah, so there is no walk from S to T in which you have even number of edges. So this one should return false. Okay. So till now you must have encountered, like whenever you are solving a graph problem, so there are 2 major ways to approach those problems. First one is reduction, and that is the recommended one. So what we do in reduction is that we changed our input graph G to a G prime, and then we use some already existing subroutines. Okay. So the benefit of this way is that you don't have to prove the subroutine itself. You just have to show the relation between G and G prime. You have to show that G prime is consistent with G, and then you can piggyback on the subroutines that you already learned in the lectures. Okay. Whereas for modification, what you do is you modify the subroutine itself. So now you no longer have a concrete base that you can actually just plug and play. So you have to develop your own algorithm. So the challenge here is that it's a little bit difficult to prove, because then even a trivial thing you will have to prove from scratch. So that's one thing. So we always recommend to use reduction here. Okay. Any question in these two things? Okay, great. So yeah, coming back to the problem. So let's try to solve it using reduction method. That means like changing our graph G to a G prime. So take some time and think about a solution. Feel free to ask for clarification if there is any. Any solutions? Yeah. So let me repeat what he's saying. He's saying like, so we have a graph G, so we convert it to graph G prime, and we label them accordingly, like with 0 and 1. And these will be odd, right? And then you run DFS on that. Mm-hmm. Okay. So the problem with that approach is that DFS it can give you any walk from S to T, and you don't control that. Actually, it all depends on your tie breaking policies. So according to that, you can get a different walk. So you might you might be lucky and you might get a walk, but it won't necessarily give you the right answer all the time. So it might miss out on the exact walk that you actually wanted. It might happen. But that's a good start when you are trying to convert your graph G to G prime. So let's see. Anyone else want to take an attempt at this? Okay. So the first thing is almost similar. We will try to convert our graph G to G prime. So here what we are doing is we are breaking our vertex into two different vertices. Okay, V0 and V1. So let's see how it will be helpful. So there are two things that you need in your new G prime. That is, one is vertices, and the second one is your edge set. So we already taken care of our vertices. So let's see how we will make the connections here. So if you have an edge from V to U such that it is labeled as 1, so you will make connections like this. That means you will connect V0 to U1 and V1 to U0. Okay. And if it is 0 labeled edge, then you will simply go from V0 to U0 and V1 to U1, right? So the interesting property here is that sum of, like for your edge total sum to be even, you need to have even number of 1 labeled edges, right? And if it's odd, then it's a odd length walk, right? So the algorithm, it goes like this. So once we have our vertex set and our edge set, then we simply run this explore on graph G prime starting from vertex S0. and we simply check if T naught is visited. Okay, looks like a pretty simple algorithm, right? But yeah. So explore is one of the graph search technique that you learned in your lecture, right? So explore, it takes two inputs, your graph and the starting vertex, and it will basically return a visited array where if the value is 1, that means the particular node is visited. If it's 0, that means it's not visited, right? So if you are able to run explore from S naught, and in your G prime, if you have a walk from S naught to T naught, that means in the end it will give you a correct value, right? If it's visited, then it will be 1, otherwise it will be 0. That means false. Make sense? Like if some of you are still not convinced with the algorithm, we can try to come up with some counter example for this. Can you think of some cases where it won't work, maybe? Okay. Let's see if it works for this example. So if we have something like this, S going to A going to B, and then B going to T. Let's say this is labeled as 1, and we have a cycle here with edge weight 0. So all of these are 0. So do you think we have a walk with even sum? Yeah, right. So yeah, okay. Please go ahead.
Yeah, if you repeat the, take the 0 edge back from B to A,
Right, yeah, that's correct. So the path, it will look, so the walk, it will look something like this: S to A to B, then again go back to A, again go back to B, and then T, right? So yeah, you do have even some path here. So let's see if our algorithm, it works exactly the way we want it to work. So the first thing is we duplicate our vertices. So it will be S naught, S1, A naught, A1, B naught, B1, T naught, T1. So S to A, it is a 0 labeled edge. That means we'll simply connect the same labeled vertices. That means S naught will be connected to A naught and S1 will be connected to A1, right? And now we have an edge from A to B labeled 1. So it will go, A naught will go to B1 and A1 will go to B naught, right? So this one is done, this one is done. Now let's take a look at this B to A. It's a 0 labeled edge. So B naught will be connected to A naught and B1 will be connected to A1. So this one is done too. Let's take a look at this B to T. So a 0 labeled edge. So we simply connect it to the same labeled nodes. So now if you are looking for, if you run and explore from S naught, it will be something like this. So it will go to A first. From A naught, it only has one edge going outwards, that is to B1. From here you have two possible options. You can go here as well, you can go here as well. And then from A1 you can go to B naught, from B naught you can go to T naught, right? So all these vertices, they are actually visited, right? So yes, T naught is visited in this case, so it gives us the right answer. Any questions? Okay, so now that we have the algorithm, we need to prove it as well, right? Because we couldn't come up with any counterexample, that means it is probably right. But we won't be sure unless we prove it. So how would you approach the proof for this problem? Yeah. Yeah, that's exactly right. So in bidirectional we have forward and backward direction, right? So what will be your forward direction? Mm-hmm. Right. So if there is a walk with even sum, sum equal sum even, that means your algorithm should return true. That's the forward direction. And your backward direction will be, if there is no such walk, then algorithm should return false, right? If T naught is not visited, then should return false. Okay. So yeah, forward direction exactly the same as we discussed. That means if there is a walk such that sum of all the edge weights is even, then the algorithm should return true. And your backward direction is, if the algorithm outputs true, that means there must be a walk. This should be walk from S to T such that sum of all the edge weights is even. Okay. So what you said was a little bit different. We said like if there is no such walk, then it should return false, right? So it was something like this. If there is no walk such that sum of all the edges is even, then return false, right? But these two statements are equivalent. So the statement that I have written below that one is the contrapositive actually. So in order to prove, you can either prove this one here or you can prove this one. Either one is fine. So basically it goes like this. If P implies Q, then not Q implies not P. Okay? Make sense? Any questions? Okay, great. So how will you prove the forward direction? Let's try to prove the forward first and then let's go to the backward after that. Maybe you can take some time and think about a strategy to prove it. Then we will discuss. So, like, what will be your first step? Like, you have already done this in homeworks, yeah. Yeah, something on that line. So here what we are, so first step is like converting graph G to G prime, right? And then we are checking for, yeah. Okay, and then we are checking if it's visited or not, and based on that we are returning true or false, right? So would be something like this. So the first one is the problem statement that we are trying to prove. Like if there is a walk which satisfies all the conditions, then we want to show that the algorithm returns true. So we can assume the first half. We can assume that, yeah. So let's say like there is a walk such that sum of all the weights is even. So before that, what we'll do is we will show that if there is a path from S to T in G, then there is a not path walk, then there is a walk from S naught to T naught in G prime as well. So what I'm saying is like, if in G, if there is a walk from S to T, then we will show that in G prime there is a walk from S naught to T naught. Okay? Yeah. No, it's not the same thing. So in a path, you cannot repeat your vertices, right? So if you have a path from S to T, that means you should not go to the same vertex again. Like only once you can, at max once you can go there. That's it. But in a walk, you can keep walking in the cycle. You can come back to the vertex. You can even repeat the edges. Everything is fine in a walk. Okay. So that's a very important distinction actually. So you have three things basically: a path, a trail, and a walk. So keep that distinction in mind always. Whenever you have a question, make sure what it is asking you. Yeah. So does this make sense? What we are trying to do here? So the question is, what does this path, what does this walk look like, right? So let's say we have even some walk in G. Let's denote it by P, and it looks something like this. Okay, the starting vertex is S, the ending vertex is T, and there are some vertices in between V1 to Vk, the intermediate vertices. And now we want to show like there is a walk in G prime as well that goes from S0 to T0. So based on our construction of graph G prime, we know that whenever one labeled edge is encountered, we go from a vertex labeled 0 to vertex labeled 1, or vice versa, right? That's how we created a graph in the first place. And we know that in our path from S to T, there are even number of ones. That means this transitions happening from S0 to some vertex labeled 1, and it's basically even, right? This even number of transitions happening, because that's how our graph is, and our algorithm is only doing that transition when we see a one labeled edge. So that means since the count of transitions is even, that means if we start from S0, we will end up at T0, right? And now we know that there is a walk. There is definitely a walk from S0 to T0. If we run the explore algorithm, we should be able to find it. Like it should return visited equals to 1 for that particular node, T0. Make sense? Maybe I can try to explain it in a different way. So let's say we have this walk from S to T in G, and let's say we have some edges looks like this: A to B, C to D, E to F, G to H. Okay, so these are the edges labeled 1. Okay, and they will always be even. Let's say there is a walk, so it has to be even, right? If the walk satisfies all the conditions, so the count of these things should be even. So if we create a graph G here, a G prime here, it will look something like this. So we start from S0, we'll go all the way here, and then at A0, since this is labeled 1, from A0 we will go to B1, right? And then we'll keep going until we encounter C1, and from C1 we'll go back to D0. Similarly, from E0 we'll go to F1, and from G1 we'll go to H0, and then eventually reaching T0. Right? So we can see like there are two distinct planes here. So whenever you are at a node labeled by 1, that means you have only encountered odd number of ones till now, right? And since it's even, so you will always come back to the same plane. Make sense? I hope this is more intuitive. Yeah. So now let's go to the backward direction. So here we are saying if the algorithm returns true, that means there is indeed a walk from S to T with even some edges. Okay. So we will almost apply a similar approach to this one as well. So we will say that, so we will assume the first half, that means algorithm is returning true. If algorithm is returning true, that means there is a walk in G prime. So keep the distinction. In the previous proof, we said like there is a path in G, but now we are saying that there is a walk in G prime. Is that distinction clear to you? Why we are doing that? Okay. So because when we assume the algorithm is returning true, that means we are talking about G prime in this case. Okay. So this walk here, it is in G prime, the modified graph that we have. And we know that the algorithm has returned true. That means we have even number of transitions, right? From vertex labeled 0 to vertex labeled 1 and back and forth, right? So by construction of graph G prime, we only do this transition when we encountered 1, right? So even number of transition happening, only we encountered 1. That means the number of ones also have to be even. So that means, yeah, if there is a even some path in G prime, then it is present in G as well. Make sense? Any questions? Anything? Okay, so now we'll go to runtime. So what is the runtime of this algorithm? Yeah, anyone? So we made the copies first of vertices, and then we added the edges, and then we have explore. So what will be the runtime? Yeah. Yeah, that's exactly right. So you are saying O of V plus E, right? Yeah. That's right. So let's see how it's coming to that particular value. So whenever you are doing this in your homework as well, try to like go step by step and show us the exact steps that you have followed to reach the answer. So here you see that, so we are making 2 copies of each vertex. So it will be 2 times V, right? Similarly, this will be 2 times E, right? And the creation will be O of V prime plus E prime, which is nothing but O of right. So this is the time it takes to just create the graph. And explore is also linear in terms of V and E. So this will also be right. And when we add these 2 things, it will be this value. Make sense? Does this make sense? Yeah. Okay. We might end this discussion session early. We solved this problem really quickly. So let's see some things like some confusion that we have observed that students make. So there is this distinction between explore and DFS that I wanted to pinpoint a little bit. So when you run explore, you take 2 inputs, right? A graph and a starting node S0. But when you are running DFS, you are actually doing it over the whole graph. So you have a starting vertex, you will run explore on that, okay? And then you will find the next vertex that is not explored till now, that is not visited. And then you will follow the same process for that vertex, and then you will find everything that is connected to it, right? So that's why the concept of CC comes in DFS, right? So it gives you like how many connected components are there in undirected graph. That's very important to keep in mind. So if you are trying to say like, if you start from a particular node and if you reach a particular node, that means you're trying to say something like explore and not DFS, right? Yeah. I guess we have time for one more problem. So let's go over that. So the problem, it goes like this: given a directed graph G, determine if there exists a vertex V such that for all vertices U, there exists a path from V to U. Pretty straightforward question, right? How would you approach this problem? Take some time to think about your approach, and then we'll discuss about it. Do you have a solution? Mm-hmm.
Search works in a way in which you can go to all the vertices and G will go into G prime, and all of the edges that
Mhm.
I just thought you guys noted OG that we were being actually this path. We're defining the vertex U as T0.
Right. So here, so in the previous problem, it was a specific node that you were trying to reach. But here in what we are saying is you should be able to reach everything. Right? So it is saying like for all vertices U. So you have this whole set. You want to find if there is a vertex from where you can go to all other vertices. But you don't know which vertex is V. That's not given to you. Yeah.
You just run that first search, and since it returns like the list of
Mm-hmm.
vertexes that are reachable, if we run it and we basically determine that the list of vertices is all vertices, then we know that
Mm-hmm.
that vertex is like existing. Is that how that works?
That's a good approach actually. So you will be running your DFS on all the vertices. That's what you're saying, because you don't know which vertex is V. So you'll have to do it for all the vertices, right? So you will go to, let's say, a first node. You will run your explore on that, and then you will calculate the number of vertices it has visited, and you will compare it with the actual vertex set. If these two are equal, then you have found your vertex. Yeah. And you will do it for all the vertices in the list. That makes sense. Any other approach? Just curious if you have any other solution in mind. So in this graph, which vertex is that particular thing that we are searching for? Even I don't know actually. So let's see. So if we follow the algorithm given by you, let's see what we ends up with. So we'll go to A. From A, let's say the tiebreaker is a random number, okay, a random node. So I will just go to this C. From here I will go to B. From B I will go to D. From D I will go to T. I will again backtrack, go all the way to A. Yeah, we can visit all the vertices from node S. So we hit our solution in the first row. Okay, we just started with S and we found the answer. So yeah. So this is exactly what we discussed. We run explore on all the vertices and we say if all the vertices are visited, we return true. And if we reach the end of the loop without hitting that particular return true, we'll simply return false. Right? So how will you prove an algorithm like this? So what is the strategy for that? Yep. How will you prove it? Yeah.
Is it not similar to that first search?
So you don't have to prove explore anymore because that's already proved. But you still have to like show, yeah.
Yeah, I mean, I was just gonna say for this one because it iterates over all of the vertices.
Mm-hmm.
The forward direction is.
Yeah. So the first thing is bidirectional proof, right?
Yeah.
Yeah. Now go ahead. Forward direction.
So the forward direction is if there's a vertex that leads to all other vertices,
Mm-hmm.
then the algorithm must return true.
Right.
Because this is like sort of by definition, it finds all of the final
That's
vertices
true.
and iterating over all of them.
Right.
So it's for sure going to find them. And then vice versa, the only way for the algorithm to return true is if there is some vertex in V
Right.
where all the other vertices are visited.
Yeah. That makes sense. Actually, that's what we are going to do in the next few slides. So forward direction is basically if there is a vertex V that can reach all the other vertices, then we'll return simply return true. So proof is pretty straightforward since we are running explore and on every vertex. So it is like an exhaustive algorithm, right? We are looking out for everything in there. So if we are able to like reach any vertex from a particular vertex, then we should simply return true. Yeah. So this proof is pretty straightforward for forward direction. Does it make sense? And for backward direction, it is basically we are saying if the algorithm returns true, that means there is a vertex V which can reach all of the vertices. So we assume that the algorithm returns true. That means we have found a vertex from where all of the vertices are explorable, right? So by definition of the return true statement, we can say, yeah, so there is a vertex V that follows this condition. Make sense? So let's take just for like this might not be the first algorithm that you come up with, right? So many times what happens is like the first algorithm that you come up with is very often wrong, right? So how do you say for sure if something is wrong? You try to come up with some counterexamples, right? And if you are sure about some algorithm, then only you go for correctness, something like that. And eventually, if that is also not true, then somewhere in the proof itself, you will figure it out that it's not right, right? So let's say we have an algorithm wherein we choose a random vertex V, and then we run explore on that vertex. And if it is able to visit all the other vertices, then we return true. Otherwise, we return false. Do you think this is right? No, right? So if you want to show it's not correct, then you have to come up with some counterexample. Any counterexample that you can think of? Yeah. Mm-hmm. Right. Yeah. So let's look at a concrete proof here. That's right, exactly right. So many times what we do is we try to come up with a concrete example, right? Wherein we can show exactly like if you run from this particular node, then we cannot reach every other vertices. So what will be that node in this case? Simplest would be to choose a sink, right? You cannot go anywhere from there, right? But there can be multiple answers for this one. Like even with C, you can see you cannot reach all the other vertices. So yeah. I guess this is all the content that I had for today's discussion. I hope this will help you in solving homework 2. The problem that we discussed today is very similar to the problem that you are solving in homework 2. Okay. Okay, great. I will be here for a couple more minutes. If you have any questions or anything, feel free to ask. And one more thing before you guys leave, we also have a second session. The content will be almost same, but if you have something that is still not clear, then please feel free to attend that one as well.